Recently we've been covering electrocyclic ring closures, so it will be useful to cover some stereoelectronic effects that can influence these types of reactions, and one of those is torquoselectivity, which is today's topic. To discuss it, we're primarily going to cover this reaction shown here, the interconversion between cyclobutenes and butadienes. What's new for today is we're going to actually look at the influence that sterics and stereoelectronics have on this ring opening reaction when we start to add functional groups to these terminal carbons, or at least terminal with regards to the butadiene group. But before we get into that, we'll quickly recap the general selection rule covering this type of reaction. When considering electrocyclic ring closures, the two main factors are whether or not you're using heat or light to trigger the reaction process, as well as the number of electrons contained within the conjugated system that you're looking at. So for butadienes, it's 4 electrons in their pi system, which would be this selection rule shown here. And by knowing the number of pi electrons we're dealing with, we can quickly see that the cyclization under thermal conditions is going to be conrotatory, whereas under photochemical conditions, it's going to be disrotatory. If instead we were dealing with chemical species that had 6 electrons, so 4n plus 2, under heating conditions, the cyclization would occur by a disrotatory pathway, whereas photochemically it would occur by a conrotatory pathway. So using this table, we can quickly see the mechanism whereby the cyclization occurs. So looking at this example shown here, we can see there's 1, 2, 3, 4, 5, 6 electrons shown, so it's 4n plus 2. Looking at our table, we can see that for thermal processes, it's going to be a disrotatory closure, whereas for photochemical processes, it's going to be a conrotatory closure. And GS here, this stands for ground state, which means heating. ES stands for excited state, which is photochemical or light triggered. With this example, we're dealing with 8 electrons now. This would be 4n, where n is equal to 2. So ground state, conrotatory, excited state, disrotatory. In this example, we've got 1, 2, 3 pi electrons, but it's negatively charged, so we add an extra electron into the system. So this would be 4. This is covered by the 4n pi electron rule. Ground state, conrotatory, excited state, disrotatory. Same example, but this time instead of a negative charge, we've got a positive charge. So if we consider our 1, 2, 3 pi electrons, we need to subtract 1 because one of those orbitals is now empty, designated by the positive charge. So this contains 2 electrons, which comes under the 4n plus 2 pi electron rule, where n is equal to 0. That means under heating, it's going to be a disrotatory pathway. If you were using light, it would cyclize by a conrotatory pathway. So back to our butadiene cyclobutane cyclization example. We're doing our reaction under thermal conditions. There's 1, 2, 3, 4 electrons. That means that this reaction is going to go backwards and forwards by a conrotatory pathway, meaning that these outermost orbitals are going to rotate in the same direction, either both rotating in a clockwise manner or both rotating in a counterclockwise manner. Because we're dealing with thermal conditions, we're only going to be looking at these 2 ground states, and we're not going to consider any of the excited states above. And this shows us the orientation of the various orbitals that are going to be in play in this pericyclic process. So if we look at the absolute ground state, or the psi1, the very bottom down here, we can see that if we rotate both of these outermost orbitals in a clockwise fashion, we're going to see destructive interference when 2 mismatched orbitals overlap one another. So this wouldn't form any bonding interaction. However, if we look at the psi2 set of orbitals, we can see that if we rotate these 2 outermost orbitals, again, both in a clockwise fashion, that we're going to get overlap of 2 orbitals with matching phase. So these would undergo a bonding interaction. So summarizing these 2 together, we get a single bond forming here when the orbitals of these terminal carbons overlap. With that background stuff out of the way, we can now go into what torquoselectivity is all about. So we touched upon that this reaction needs to undergo cyclization following a conrotatory mechanism. So these outermost orbitals need to rotate in the same direction as one another. However, this rotation could be counterclockwise or it could be clockwise. Now, if there's no R groups, it really doesn't matter which way is chosen. But when you start adding different R groups that have steric considerations and stereoelectronic effects, these R groups can influence which direction the orbitals are going to rotate. Now, the effect of these R groups is felt most strongly on the activation energies. That is the trigger whereby the bond either starts to form or starts to break. In the diagram, we're showing two examples of what could occur when we break this bond, rotating the orbitals in either direction. So in the top example in blue, we're going to start rotating these two outermost orbitals in a counterclockwise direction. So in doing so, this R group is going to rotate inwards. This R group is also going to rotate inwards. And when this bond breaks and it forms the products shown over here, we can see that the R groups are actually clashing with one another. So sterically, this final product can't adopt a planar configuration because these R groups would overlap with one another. That means this form shown here in the box is suffering from steric repulsion between these two R groups, and the entire chemical structure is relatively strained. If conversely, we look at the example shown at the bottom, we instead rotate both outermost orbitals in a clockwise fashion. This time the R groups are going to rotate outwards, delivering what we can hopefully see is the sterically favoured product out of the two. So here, this product can be completely planar. There's no steric clash between the R groups like up here. If we were considering this reaction solely in terms of reducing steric clashing, we would expect that the bottom pathway would be preferred always. However, there are situations where the top pathway is actually the preferred pathway, and this is based on stereoelectronics. So let's focus on these electronic and stereoelectronic effects. As we've stated, different R groups are going to influence the direction that our conrotatory motion is going to take. And whether or not the R group donates or withdraws electron density is going to have an influence on that rotation direction. So shown is a good example of torquoselectivity. Starting from a single starting material with an R group, if we vary what the R group actually is, we can completely control where the R group will be located at the conclusion of the reaction. So if our R group is a methyl group, for example, the only product we would see is where the R group rotates outwards, giving us a conrotatory out or con out product. If, however, our R group is an aldehyde, so something that's electron withdrawing, this time we only see the product where the R group or the aldehyde has rotated inwards. So this would be a con-in pathway. Let's look at why this is. So con-out preferred reactions occur primarily when the R group is an electron donor. So things like methyl, which is relatively neutral, chlorine and methoxy groups, and we're going with a chloro group in the example. So given this structure, if con-out is preferred, both of these orbitals at the terminus need to rotate counterclockwise to get our chlorine group towards the outside of the molecule. If we were to look at this molecule following this direction of gaze shown here, so looking directly at this bond, we can see the reason as to why this is down here. The left is showing the con-out pathway, while the right is showing the con-in pathway. For con-out, if we look at the bottom structure, which is the highest occupied molecular orbital, so effectively this is the bond that we are breaking here, and we've just twisted it enough that these two lobes are starting to come apart. We can see our chlorine, the electron donor here, and it's simply moving away from this bond and not really influencing it at all. So this argument is primarily all about sterics. Moving the chlorine in this direction shifts it away from this bond, not particularly stabilizing or destabilizing it. If we instead look over here at the con-in pathway, if we take our chlorine group and we start to rotate it inwards, we can see that we have the two lobes of the bond we are trying to break, and we're bringing towards it a full orbital with a lone pair inside of it. Because this orbital is full, this electron here can't really interact with it. So effectively this becomes a destabilizing interaction, whereby there's a repulsion between the electrons in the bond that's breaking and the full orbital containing the lone pair of electrons that's moving towards it. And if you remember, this torquoselectivity, it comes down to activation energies. So this is what's occurring at the very beginning of the chemical process. If there's any form of repulsion here, you are going to increase the activation energy to take that pathway. So this small repulsive 4-electron interaction here is enough to disfavor this pathway using an electron donor. Whereas over here in con out, there's only a sterically favoured argument for that process. If we now consider the pi acceptor R group, where con in is going to be preferred, this is favoured by R groups such as nitriles, aldehydes, anything with a pi acceptor group. And we can first consider con out because it's basically exactly the same as in the previous example. If we have this large bulky functional group moving outwards from the core of the molecule, there is a steric argument to be made that this would be favoured, which means that there has to be a stronger influence favouring con in if that's going to be the preferred pathway. So here we're looking at the aldehyde. We've drawn a con in pathway whereby the outer two orbitals shown here are going to rotate clockwise, bringing the aldehyde inwards. We're going to look along this direction like we did before, shown here. And if we consider the pi bond of the aldehyde, in particular the pi antibonding orbital, now instead of having a full lone pair orbital, we've got a larger antibonding orbital with a single electron in it. This is going to offer a stabilizing force as we start to break the bond beneath it. So effectively, this aldehyde leaning closer above this breaking bond is actually going to lower the activation energy of this pathway. And it's important to consider that this attraction is occurring right at the beginning as this bond is breaking. So there's none of the penalties at this point that we are going to see later on when we enter into the final products and the product is relatively strained. Essentially, there's stabilization as the molecule is committing to undergo the reaction. And then when it gets to the end, it gets the penalty then. So here's a good noteworthy example of torquoselectivity in action. In this starting material, we have two R groups. We have a tert-butyl group, which is going to be by far the most sterically bulky functional group. And we have our electron donor group, which is a methoxy group directly next door to it. So, as we've just seen, if you have an electron donor group, this is going to preference the con-out pathway, meaning that even though we have a very bulky functional group that sterically would probably want to be on the outside of the molecule, because of these electron lone pairs, those are going to influence the activation energy, placing it on the outside of the product that we see. So indeed, when we heat up this material, what we see is that 99% of the product, we have this methoxy group oriented outwards, and our bulky tert-butyl group is oriented inwards. Now, if we were to repeat this reaction, but replace the methoxy group with just a methyl group, which is more neutral, it's not much of an electron donor, repeat the reaction, we see that this time the tert-butyl group dominates the outside position, so essentially sterics win in this lower example. It is worth noting though that methyl is a slight electron donor, so 30% of the time it does actually find its way to the outside position. Just before we finish, it's worth considering one other hyperconjugation effect, just to show how much influence torquoselectivity can actually have. So if we consider this starting material here, where we've got two very bulky silyl groups on the outermost orbital positions, if we were just looking at this molecule, because of their steric bulk, we would almost certainly guess that it's going to form this con-out pathway. But in reality, only 22% of the product will form this less sterically congested product. Instead, we see 78% of the strained con-in product, meaning there has to be some sort of pi acceptor behavior occurring just as this bond here is breaking. And it turns out that hyperconjugation of the sigma antibonding orbital between the silicon and whatever the R groups are is creating this empty orbital directly above the bond that's breaking, stabilizing it when the silicons are moving inwards like so. So effectively it comes down to what orbitals are surrounding the breaking bond, and do those orbitals stabilize or destabilize the activation energy? So that's my quick overview of torquoselectivity. For me, it's about appreciating the stereoelectronic effects that give rise to these really strained butadiene products when pi acceptor R groups are present. This certainly goes against what I expect to be the primary products that you would see when you're dealing with sterically bulky groups, and really shows the importance of understanding the orbital configuration around the breaking bonds in these pericyclic reactions. Just as a quick note, we've only really covered in these examples the 4n conjugated pi systems under thermal conditions. So there's still the 4n plus 2 and the photochemical processes to wrap your head around. That's it for today. Thanks for watching.